Heat losses are an inherent part of any real process, commercial or industrial. With losses, I mean here amounts of energy that is available but not used. And this energy is not only wasted, it's a resource we're throwing away, but it's also a source of contamination if transmitted into the surroundings without proper treatment. It can come from any kind of process, from motors and air conditioning to cooling systems. Heat losses cannot be completely prevented. Even if we have energy efficient components or optimum insulation, they are always going to be there. Nevertheless, we can reduce them significantly. And even if the carrier gets emitted, the energy that it carries may be diminished, and therefore the thermal contamination also reduced. Temperature translates into quality in terms of heat. Waste heat has generally lower temperature and therefore lower quality. Nevertheless, it can be integrated directly or indirectly in many different stages of the different processes and units. Therefore, if integrated, one can achieve not only higher efficiency, but also more or increased profitability for the given process. In Germany, for instance, the thermal potential of this waste heat goes up to 125 terawatt hours per year. This energy integration implies modifications in the infrastructure and also an increased complexity for the processes that are integrated. This translates into higher investment costs in reality. Nevertheless, these costs are repaid in a given period of time. And not only the profitability, therefore, it's accounted for, but also the input and the contribution through the operation, through the entire life cycle of the process of the machines. A concrete approach of energy integration is the so-called waste heat cascade.
Germany is one of the leading industrialized countries in the world. For production and processing, its industry requires more than a quarter of energy used in this country. However, a high proportion of this energy is lost as unused waste heat. This potential is best realized along the so-called waste heat cascade. At the top of the cascade is the avoidance of waste heat. This avoidance can be achieved by optimizing the design, for example by converting a vertically loaded furnace into a laterally loaded furnace. In this way, far less energy is lost to the environment when the furnace is loaded. Furthermore, the loss of heat can also be avoided through single insulation. In addition to prevention, the use of waste heat in the process is a very efficient measure. Here, the hot exhaust air from the furnace can preheat the cool air supply in a heat exchanger. The preheated air then flows into the combustion chamber of the furnace. In this way, the air-gas mixture reaches a higher temperature before ignition, thus saving energy. Another important step in the cascade is the on-site use of waste heat. Without compressed air, the machines in many factories would come to a standstill. And compressed air is generated with the help of electrically powered compressors. However, only 3% of the electrical energy is utilized for generating compressed air. The rest is lost as waste heat. Special compressors can use this waste heat with the help of a heat exchanger, for example to heat galvanic tanks in the company. By utilizing the waste heat, instead of only 3%, up to 70% of the energy can be used. Another example of the internal use of waste heat is provided by combined heat and power plants. In a combined heat and power plant, a combustion engine produces electricity and additional waste heat via a generator. A so-called absorption chiller can then convert this heat into cold in a special process. And this cold can then be used in the production process. If the waste heat is available at temperatures above 200 degrees Celsius, it can be used to produce the highest quality form of energy, electricity. In a metallurgical smelting process, hot exhaust gases escape. A heat exchanger can absorb some of the energy, which flows to a so-called organic ranking cycle, or ORC plant for short. This ORC plant converts waste heat at a temperature level of 200 to 400 degrees Celsius into electricity with an efficiency of 15 to 20%. Via an additional heat exchanger, the waste heat can also be used for non-operational purposes. In this case, the waste heat can be used to heat a large buffer storage tank, for example, via a well-insulated pipe system. An external service provider then uses the stored energy to supply a nearby housing estate with heat for domestic hot water and heating. And he does this independent of the production processes of the company. The potential for waste heat utilization in German companies is great. Practice shows that this potential is best realized along the waste heat cascade. The stages of this cascade are avoidance of waste heat through, for example, design measures. Use of waste heat in the process, for example, to preheat combustion air. Use of waste heat in operation, for example, for an absorption chiller. Conversion of waste heat into electricity, for example with the aid of an ORC plant. Or the use of waste heat outside the plant, for example for heating buildings. The technologies are well known and have proven themselves in practice. Using waste heat pays off and protects our climate.
In order to support and leverage this first phase of investment for the projects on energy efficiency, the German government provides funding. The central program for federal funding is the Program for Energy and Resource Efficiency in the Industry. With this program, the German Federal Ministry of Economic Affairs and Energy aims to reduce the emission of CO2 by increasing the energy efficiency and reducing the consumption of natural resources. The program supports, for example, the investments in heat exchangers for recovery from processed flow water and other heat-carrying streams. Operations require special attention to specific characteristics, such as the low temperature gradients and the non-optimal transfer coefficients. These kind of measures are subsidized with a rate up to 40% of initial investment. In the same line, the program supports energy-related optimization of plants and processes, not only for heat provision, but for the application and adaptation of the infrastructure in plants and houses and buildings. These adaptations include, for example, pipelines, which are responsible for most of the investment costs in these kinds of applications. Also, direct conversion of the heat into electricity by means, for example, of organic Rankine cycle. The subsidy rate for these measures is up to 50% of the eligible investment costs. So far, this funding scheme has been well received in the market, with up to 21,000 funding applications in the first 2 years for increasing the energy efficiency in the industry. Overall, 25,000 measures are expected to be implemented by the end of 2023, implying reductions of up to 3.5 million tons of CO2 per year. In this way, the German government supports technical measures through policy instruments that the industry to leverage its energy efficiency potential, as Germany aims to achieve greenhouse gas neutrality by 2045. Policy instruments of this kind are an important contribution to achieve an energy-efficient economy and to reduce the consumption of primary energy resources of the country.